Awesome.
Okay,
So yeah,
cool. Let me give a very brief intro at the beginning, just
perfect. Thanks.
say a few words. So hey everyone, welcome. I think this is the last seminar series of this whole semester. So thanks everyone for joining. And today we have Dr. Jonas Frey. I hope I pronounced correctly.
That's good.
From Stanford across UC Berkeley. So he's currently working with Marco Pavonian at Stanford, and also collaborates a lot with Jitendra and Sanka Sastry at UC Berkeley. So I actually met with Jonas briefly, when I visited Berkeley late last year, and we have some conversation there. And interestingly, I start to learn that, I know his work at ETH before that, and then Sankan actually pointed out, the author is here, so I feel it's okay. This is a very good time to talk about some of the more details, largely driven, by the work led by Zewon. So it was a very fine, coincidence and have, the authors, in the same room. Eunice work a lot on like the navigation, perceptive locomotion, as you can see, on the screen. I think before that he worked with Marco from ETH. I think have a lot of cool work on this animal, like the robots. Today just as the title indicates, I guess he would talk a little bit more about this embodied intelligence and how to build this general purpose autonomy. Um, Thanks, Eunice. Let's start with this very cool talk.
Awesome. Okay, yeah, thanks a lot. Thanks a lot for the introduction. So yeah, as the title says, so my interest lies in kind of like building systems that are more autonomous, that can navigate spaces that we couldn't do before. And to just get started a little bit, I bring you here like these two videos from my lab that basically happened before I joined. So on the left, you can see this animal bee robot that was like developed around 2014. And this is controlled by like model predictive control. And we could see like the first steps these systems are taking and walking over like these kind of semi-structured environments with like these industry sites. And they were like the first hope basically within our lab of like, okay, these systems really going to change how we see the world or like how where we see like robots in the future. And then it took a few years later that we kind of had this really step function in terms of capability of those systems by introducing like reinforcement learning to control those robots and make them walk in these like super rough outdoor terrains. So basically all this work was done by like amazing people before I joined the lab at ETH Zurich. But it was really inspiring to see of like what a crazy level of improvement we have achieved. And now if we would put like another video today, we see like humanoid robots doing backflips and all kinds of crazy things. So I think we have gone like a really long way in just a very small time period from starting my PhD towards where we are now. But I think when I started my PhD, basically those two systems had both in common that they require kind of a human teleoperator that guides the robot to send it around and navigate within an environment, which is basically the problem that I want to be working on is to really like gain value out of those systems. We need to overcome kind of like this problem of autonomy and intelligence within them. So my research really focuses on like how can we use those robots for different applications. So from disaster response to like delivery of packages, using them in like daily life. So I think for the future we will see like all packages being delivered by robots towards your doorsteps, or for example, using those robots in applications like monitoring of natural habitats. And basically this is the mission that I try to achieve in my PhD, and I'm also currently working on as a postdoc, is really enhancing the autonomy of those systems in the wild here. And to achieve this, we can look at that we want to have these different applications growing. But at the same time, I would argue to kind of deal with these complex environments we can now operate those robots in, we really need to think about like having learning systems that can address these complexity in the real world. But at the same time, I think like one thing that's very important in the research I've been doing is grounding those things in kind of like first principles. So with first principles, I'm not meaning the underlying physics, but more like a really good system understanding of the system that we are actually controlling. So we should understand the dynamics, the embodiment, kind of like how this translates into the design of those learning systems, which we will see like in a few cases later on, but not at the start. So as said, the slides were kind of shuffled together, but I want to show you basically the latest of the latest that we have released since 2026 for today that you get a little bit of this feeling of like what's currently going on the research agenda on our side. And then we look a little bit at these works that these things are building up on. So we do like the reverse. We start out with the interesting stuff that is like brand new and like just have been accepted to conferences or even under review. And then we look a little bit in like some works that we you have even made like some extension to this and hope that helps some students before. Uh, so to get started talking a little bit about this for like this autonomy for navigation, I think it helps to just quickly define this general scope. We have like a robot with a specific embodiment. We want to achieve a certain goal that involves like, for example, navigating towards a certain place. And then we need to find the safe path that leads us there. But when we look at this problem, basically, like the robot on the left clearly has a completely different way of navigating its space. Like kind of how the world for this robot looks like is very different to the robot on the right that has like this advanced kind of navigation capabilities that's potentially stronger. So basically, when you think about like planning or like navigation in these environments, it clearly depends on the terrain we're walking over. It depends on the hardware, so kind of which capabilities do the robots have. But also it depends on the underlying software we are using to run on those systems. So we really need to build kind of like these learning systems that account for all three of those aspects. And one of the essential parts basically is kind of thinking about can we introduce a taxonomy? So this taxonomy I will be using over the talk, and we can try to categorize a little bit the works that we're doing within this framework. So the first thing is basically we want to learn basically how to navigate based on estimating a sort of traversability, which is this abstract notion of having a cost that we can associate with a certain part of the terrain in the environment. So the idea is you assign a cost value that could be a scalar based on an observation that could be an image that the robot sees to a certain region in the environment that helps you to avoid like risky places. Then there's a more implicit form that kind of like mimics kind of representing this traversability, but not explicitly saying for a certain part in the terrain, like what is the traversability score? And that would be, for example, you try to predict a sequence of actions that, given an observation, leads you towards like a goal. And therefore, we implicitly encode this like notion of traversability. And lastly, like one interesting part that we have just like recently been starting working on is actually this notion that falls more in this like world model setting, but we call this like a forward dynamics model, or we just like look at a very specific part on like studying these dynamics of those systems. So kind of what is the future state of the system it will be in after we have like starting out with an initial state and we apply a sequence of actions. So it's kind of the inverse problem that allows us to then like use this with respect to like a planner. So for today, we see like kind of like some works that fall in all of those categories. Uh, but before this, I want to give you like some understanding of kind of like the tools or the modalities that we're using in those systems very often. And one of the like most important modality for us is actually like geometry, because geometry is something that is really good for navigation. It generalizes between the simulation and the real world. But we think it kind of like is got a little bit of like underappreciated in some recent work, because I think we are not using kind of like the way we should use geometry to its full extent, because we're missing like good foundational representations for that. And what we did in this work is actually we tried, or like basically this work was led by Mantan here. We tried to figure out, can we train like a feature extractor for depth representation? So we see that for images, we have these like amazing tools that allow us, you have an input image, you can extract a certain set of semantic features or features like dino features that represent the world really meaningful. And therefore those like models generalize to a variety of different settings. Now, when we train the same thing in simulation, we actually don't see these effects happening for like the policies that we're using today, because we just have a lack of geometric data for training those systems or doing like this large scale self-supervised training. So we tried in one recent work where we are very fortunate in Switzerland that we have access to thousands of GPUs to train such a foundation model that can take, for example, like a lot of different depth images as an input and then provide like meaningful semantic features. And what we saw in this work, that we can basically get to the same effect, that we have kind of like features based on depth images that are associated with certain parts of properties and that generalize across like different sort of data. So here we can see that the handle of these mugs that we see the depth images here on the left, they are like consistent across kind of images for different images recorded with different sensors. And we can see that some sort of like latent features are then embedded about like the rim, the mark. And when the assumption is when we use basically such a feature extractor network for like the depth dev images, that the policies that we try to learn downstream based on those features that we're using will be way more powerful. Uh, and we basically showed this for a variety of different tasks. So we look kind of at this dev image, um, for dev images across like tasks that require you to classify things on ImageNet, which is a standard benchmark of understanding how well your feature extractor works. We also looked at the same thing for kind of semantic segmentation tasks, where we saw that actually if we do this large-scale pre-training based on a Dino-based pre-training regime, we also see this level of improvement for dev images. And we also looked at then how does this translate to a variety of different robotics tasks, where we looked at kind of navigation, manipulation, and locomotion. So we tried to really see like, okay, the policies that we now can train in simulation using dev as an input, will they generalize better if we start out with a better and pre-trained feature encoder? And what we saw in kind of like this navigation case is that these policies then obtain like a better performance in terms of like understanding the scene and knowing where to go and how to navigate. So here on the left, this policy is trained with like the default way how you would kind of interpret dev images before, based on a VAE. And on the right, we see our policy. And basically, on the left, we can see that this policy at some point here fails, that it cannot navigate around and correctly recover, while our policy obtains like a better understanding from the dev images, can use the feature and the understanding of this thing being a fence to successfully avoid like navigating to these places. We have then shown that basically this method we can then deploy across like a variety of different scenes from like outdoor, indoor scenes. And given that the features that we extract are so generalizable, given that they have been trained on like millions, so like around like 30 million different images that we collected from the internet of dev images, they will generalize to a variety of different scenes that we have not seen before. Uh, so we deployed that system then. Here just is like some reference across a variety of different tasks in like outdoor, indoor environments for like long-range navigation of that system, where it's then like a standard reinforcement learning policy that we train but using our features compared to like the other features that we or like the other dev image encoding that we have seen before. We also tried the same thing out, for example, here for manipulation, where we then saw that, for example, the representation that we could learn with getting access to the features that we extracted based on this large-scale pre-training is way more robust for handling like noises in the image and other things, where previous methods were then completely like out of the distribution and could not handle kind of like these manipulation tasks anymore. Um, Similar, we did like some examples where it's actually super important for your skills to have like really good geometric perception. So for example, in this ladder climbing task, you need to really nicely identify and understanding where should you place your feet. And we saw that kind of like using these like large scale pre-trained features also for that task, when we input 6 cameras into kind of like this policy here, and for 6 of those cameras, we extract those features based on our pre-trained model, we obtain a significantly better result and performance. So basically, this work is now like open source available with like everything documented here on this web page, where we provide basically a family of different depth image encoders across a variety of different sizes and scales. And they're basically pre-trained on like 60 million depth images that we collected from the internet in a self-supervised manner, very similar to Dino V2. Um, and then also we distilled them into like super small and compact CNNs, such that you can use them with like reinforcement learning in your simulation environment. And we showcased really precisely that these features cover so much more that you would expect is not in the depth information about like the semantics about the environment, which is a pretty cool finding, I would say. So like this is currently like under review for TRO, but I hope we get like some feedback quite soon. And the full system achieves basically like state-of-the-art performance in terms of like feature extraction for those dev images. Uh, so yeah, we have shown then basically in all of the real-world experiments that you can plug it in into like any sort of sensor, and the features that you extract maintain that will stay meaningful. And we did not do anything specifically for like the navigation tasks, the manipulation tasks, or all of the other robotics tasks, but we just used the pre-trained feature extractors to fulfill those tasks. Very similar to what we see now in the computer vision domain. Uh, yeah. Then like one of the next works that is also very recent with a kind of a prop change here is a work where we looked at how can we kind of use like these foundation models for doing like navigation in like an open vocabulary setting. And this work is called like WildOS, that is also currently like under review, that we work together with NASA JPL, where the overall idea is that you want to have a human being able to tell like your robot, okay, go to the NASA logo here and search for this in that environment. And then the robot should basically like have a rough understanding of where maybe the goal is, but then be able to like search for kind of like the NASA logo here and go closer and closer towards the NASA logo until it reaches the logo successfully. Uh, and I want to walk you just a little bit through like what it takes to build such a system today, or what we developed here in collaboration with NASA JPL. So the input of this system looked as follows: that we have kind of like a goal query of what we would like to see. And then we have an RGB image that the robot has constantly access to, that we can access and retrieve the information. We know where the robot is, and we have access to sort of a traversability map of the environment that describes where the robot can be going. So if we look at a little bit the data that is collected, you can see here there's an elevation map. And from this elevation map, you can derive kind of where you can navigate within this environment when it's a very structured and simple environment. Based on this, we can basically we can basically extract a graph based on this elevation map and put it together. At the same time, we can use the image observation that we have available on the robot to extract where we can walk from the image information to understand kind of what's the visual traversability of the image. But at the same time, we can extract this concept of visual frontiers, where you can see here in the kind of top image that there are certain regions in your environment at your horizon that it's very promising to explore. So we basically combine like a traversability estimation with an estimation of where it's like promising in an environment to explore, which is very similar to how a human would be behaving. You can look at an image and then you can tell kind of where should you go in that scenario or on that image that leads you towards the goal. A fun fact here that's is basically that usually these regions that are good to explore are between like the horizon and the last traversability space. So this is why we think also, because we trained here a very small model on a very few samples, we found that this generalizes really, really well just because of this case, because usually these regions are between the horizon and kind of your last bit of traversable area. And at the same time, we kind of used like here a foundation model for kind of language conditioned image or language conditioned image features that we could actually like also retrieve kind of where's the information of this NASA logo from those features by checking like the similarity between the image features and our query prompt. So this way we have a single model that allows us to obtain where's kind of like our goal object, or can we see a goal object, where is our what's our visual traversability, and at the same time where's a good place to explore. Uh, Based on this, we then obviously could localize kind of the object that we're looking for based on a particle filter by kind of fusing those informations together. So we can use the baseline of how the robot navigated without having access to geometric measurements to at a very long distance already like triangulate where the goal is. Um, and then we combined basically the geometric traversability together with the visual traversability to guide the robot throughout this navigation graph that tells the robot, okay, where should you explore and where is like a high value region for your system to explore. And the interesting part is by combining this visual traversability, we can see significantly above the geometric range, because the geometric range of the robots are usually confined to kind of like 10 or 15 meter, where you have really dense geometry available. But with the vision, you can see like hundreds of meters ahead to already plan where's a good location to go. And basically, by combining those two things in this mannered approach, we found that we get quite some cool behaviors out of the system. So we tested this for like these long-range navigation tasks, and we saw that by combining this like graph representation, visual traversability, and geometric traversability by scoring frontiers in this specific manner, that we could see that the robot can go to dead ends, recover from that, turn around, and even explore from a long distance already the right promising routes, and not being able to like get stuck in local minimas. So this hybrid approach was very cool to see and how it works, and also that we could ensure that we have some sort of formal guarantees of that we can explore the full environment. Uh, okay, then
I have a quick question.
yeah, sure. Go.
Yeah, sorry to
You want to
interrupt.
ask? Yeah.
So when you combine the visual traversability and geometrical traversability, how do you
Yeah.
combine them into one graph?
Yeah. Very good question. So we always combine basically from a visual traversability. We could go into the image, and we see here there's a frontier in the kind of visual frontier. And what we then did, we kind of traced on the visual frontier the path towards the closest geometrically accessible node. So we can basically combine those two things together to score based on the visual frontiers, the geometric nodes. In terms of where the robot navigated, we basically use this visual traversability solely to understand where you should navigate. We did not use it in the underlying traversability analysis because for the terrains that we looked at now, the geometric traversability was always our ground truth because we did not go in these like fully unstructured outdoor environments. So kind of we said like for local safety, you always use your geometric traversability, and then you try to use your visual traversabilities to score and get an understanding of where you should navigate. Yeah.
Oh, so for more global planning, you use visual traversability, and for local safety, you use geometrical traversability.
Exactly. Because then we usually have enough geometric data available to make a safety assessment. While for
Right.
things far out or at a long distance, we don't have enough geometric information available. Yeah,
Yeah. Okay. Thank you.
awesome. Okay, yeah, feel
So,
free
so
to throughout
quick,
the
quick, quick
talk always ask
question.
questions. Yeah,
Yeah, quick question. Yes, this navigation graph, it's for more for both global and local planning, or and how, or just maybe one of it, and
yeah,
then how
yeah,
you, I assume it's updated in online fashion, right? Not just a one-time build.
yeah,
So
yeah.
how frequently it's updated?
Yeah, so we updated at 10 hertz. So you constantly update the graph. And this is basically an implementation that's now publicly available. It's done in C++. And Patrick, like my collaborator or our collaborator at JPL, basically implemented this graph. And the cool thing is that this graph is basically coupled to your odometry of your robot. So if you get an update in terms of your odometry estimation or you obtain a loop closure, then all the graph will deform and basically cover your updated poses. So it's a very nice system that you kind of add new nodes, always with respect to your local odometry reference, but this
Mhm.
allows you to deform the full graph at a very high speed. Yeah, and
So
it's
I
a
can
full.
treat it kind of more for local planning, and where the end of the graph is kind of the frontier. Is that
Exactly.
correct?
Exactly. But you can also do global planning with it. So
Mm-hmm.
given that this graph is so implemented so efficiently, you can grow it up to like millions of nodes and you will be still able to kind of like run a star on it or like other things that you can get like a very good local waypoint out. So I
Mm-hmm.
would see it's like kind of like how effectively what we were running is in this example. There's basically like a global waypoint always extracted in like 2-3 meter distance, and then the robot with its local planner goes to this next 2 or 3 meter away waypoint. Uh, so it's basically provides you we can set different thresholds of like how small we want to have the distances between those nodes and edges in this graph. But
Mm-hmm.
yeah, it's basically a global planning graph. Yeah.
Is it open source already or not yet?
Yeah, this is open source available. So
Okay.
if you search for the paper, it should be already in there. And it's under the NASA JPL GitHub repository.
Okay.
Yeah,
Sounds good. I think we
yeah.
have people interested. Yeah.
Awesome. Okay, yeah, that's very cool. Yeah, it was a big struggle for them to make anything open source at NASA. It
Yeah.
was
Yeah.
took us some time. But yeah. Uh, No, yeah, there's the project webpage. I was like, sorry, I have not the links, I have not the correct citations. I think I wanted to clean it up for the next like two hours. But I will send around if you want an email with a little bit of the references that are maybe useful for people to use. Uh, yeah. Uh, should we continue or do we have like a few questions on that here?
I actually do have one question.
Yeah.
I was just curious as to like how much of the framework is sort of tied to the spot embodiment. Like if you wanted to swap in a different quadruped, how
Yeah.
much of that planning? I assume a lot of like the foundation model stuff would be sort of platform
Yeah.
agnostic, but in the planning side, do you have to, are there considerations you have to make?
No, I think not. It should be plug and play. So like the only thing that basically is not fully agnostic, or like the only thing that's not agnostic is the traversability estimation. So when we kind of like obtain like this map representation here, wait, it should be on that slide. So if you obtain that map representation, you can see there's like certain heuristics that are applied based on the geometry that tell you which space in the environment is safe. This would be the white space, and which space is like untraversable. And that might look different for like a wheeled robot or for like a smaller quadruped or a bigger quadruped. But basically everything else is completely agnostic. Yeah.
And is there like explicit foothold planning done if it needs to step up onto a curb or something like that?
No, no. We assume that basically the locomotion of the robot is quite capable. So like this runs this default spot locomotion policy. So this will just walk over a curb. So then the curb will look here in this environment like just fully traversable. So there's also like no strong, smaller, fine-grained preferences that are included in this representation here. So here for us, the main research focus was really how can we kind of have like this combination of visual traversability or visual object goal search at a really, really long distance beyond your geometric range and combine this together in such a framework. Yeah.
Cool. Thanks.
Okay.
I have one last question before
Yeah,
we move
sure.
on. Yeah. So, what happens, for example, if there is a visual goal, but like, and it's in front of the robot identifies it, but like, let's say in the road there's construction and it has to take a new path, which means that it has to move away from the visual goal, like it can't see it anymore. Like,
Yeah.
does that kind of scenario be handled easily with this kind of framework?
Yeah. This scenario is actually like something that we perfectly cover in that system. So the idea is that kind of like this graph representation that we have here, that functions kind of as a storage of like where is it interesting to go. And given that the graph kind of encodes, okay, there's kind of like a very high or like a really fruitful area to go in terms of your visual traversability tells you you should explore towards like this region here, or like this region here in that case. We can even remember what we have seen before. So if we end up here, when we go this direction, we see when we get very close, okay, actually there's like a big height step that would block us to actually move here. We would still remember, okay, we can go to like the second frontier and then try to explore to walk around here. So you can have some formal guarantees that you explore all of your environment in such a setting if you build up such a graph. Uh, and we basically use the graph as a memory for storing all of the previous predictions and informations that we have gained from the environment. So this was actually
Thanks.
something very specific for like they had like a big project with searching for people that are lost in different places and wanted to explore a house that you see in the horizon and other things, but it was super hard to reach. And you, this was actually exactly the example we tried to also solve with the system here. Yeah. Okay, perfect. Then maybe I talk a little bit about like the next project. So this one is currently under review for field robotics that you have seen before, and this one is under review for RSS. And this was done by a master student at ETH that now will come to Stanford, and we call this like less is more. And we had this underlying idea of this work was actually looking at wind. So wind or nomad, these are like these foundation models that basically have this like big promise for like visual navigation or navigating from images that you can take as an input a set of past observations, so your 5 past observations, and you can specify a goal by just having like a goal image provided to the system. And then you have directly like an end-to-end network that you can train via imitation learning to predict the normalized actions and maybe like a temporal distance towards your goal. But the key was really like just predicting your normalized action. So this falls very nicely into the works that we see in like the manipulation area space, where people just use like imitation learning to drive the learning process of these models or of such kind of like navigation model. And the interesting part in this work was basically like it's a very simple, scalable way to train your navigation behavior, right? You just need to have like a big set of data of like your system or different robots walking around, navigating the world. And then you can train something in a really scalable manner because potentially this data is cheap to collect and easy to have. And we basically want to infer based on our past observation a little bit kind of which embodiment we are controlling and what robot we are using. Uh, And then also one thing is that kind of like this learning across embodiments was something that's like promised here in this work that makes sense to like learn and transfer knowledge between different embodiments on how to navigate the space. And then in the community, I think now like also this was very transparent by Dhruv and all the other authors that this is kind of like a really nice idea, but when it practically comes down to like deploying those systems, they're very fragile, like super, super fragile. And what we found is basically that kind of training across those different embodiments may be really not the right thing. So for us, kind of when you think about a legged robot, as you said previously, like how well does this generalize? A legged robot should just behave very differently to a wheeled robot. And I think really this concept of how you interpret your environment should be something that's very embodiment specific. In philosophy, there's this term of Umwelt, where Umwelt means basically how you interpret your environment should be very agnostic or should be very specific towards your specific embodiment. Also, what we found kind of in this work or studying this was a lot that kind of the imitation learning data that we have, even for those systems, is super, super sparse. So you have like a completely like weird distribution of actions that you take because most kind of teleoperation data that you have is like going straight forward and you have maybe like a few turning left and turning right. And the data, while being considered very big, is actually super small compared to complexity and different environments when it comes to navigation. In a tabletop scene, when you do manipulation, you can imagine the table very often does not change. It's very consistent and you have to do the same thing over and over again. And you set it up in a way that you have always like a static camera around, you have a risk camera, that you have kind of like global context available and you make your problem as observable as possible. And in the navigation case, this is inherently not the case, and we need to have really formed this like long context memory and this good understanding of the environment. And we found simply that these capabilities are absolutely missing in those policies. Uh, there's also like a really nice adjacent work if you're like interested in this visual navigation. It's called data scaling for navigation in unknown environments, where they basically showed like most design decisions ever done don't matter really of like how you train those systems. And also they showed that basically the average success rate across all of those policies, if you try to navigate 100 meters in a not cherry-picked scenario, is around 50%. So this is like when you think about deploying those systems in any way, like going 100 meter and you have like a 50% success rate is super bad. But at the same time, we see that some of those trends are actually like used right now in self-driving, that actually like Tesla or so uses imitation learning driven objectives for self-driving. And there they have basically access to infinite amount of data. So I would argue that we want to have the same capabilities of like really good visual navigation, but with significantly less data than Tesla. And I would say we need to have like really rethink the way we kind of generate data. And this is something that Yves did here in this work, where we basically looked at can we bootstrap significantly higher quality data from like the existing systems that we know that work on robot. So here's like a data set that I will show you later a little bit to you. It's called like this Grand Tour data set, where we have like an imitation learning path. So like we had like a human teleoperating around the robot. So you can see the red path is what the robot actually went. And then we can see that we can just select the goal in this future path that we actually want to walk. But by doing so, we will end up with a data set that's super biased towards walking straight forward. It's not really like super diverse, and you need to infer all of this complexity about your environment, how you should navigate, how you should interact, based on a very sparse, like two-dimensional signal of the direction and velocity you're going at. So it's a super hard learning problem. So what we kind of suggested instead is that we can leverage other information that we have on those systems to generate more high quality paths that have like higher diversity. So we can, for example, select new goals that we try to achieve and then have like a geometric planner that allows us to plan to those goals based on like such a height map, for example. And therefore, we can increase basically the data set diversity like a lot. We can also kind of use the full holonomic like motions that the robot can do based on how we set up this geometric planner. But for a lot of environments, actually, we have really good planners available. So the idea is, can we get like the knowledge that we have in those planners also in the imitation learning policies or these visual policies? So we distill something that requires us to build like have expensive sensors to build like a geometric map around the robot and then basically do all of the like planning. Here in this case, this would be MPPI planning to obtain those paths towards the goal, but distill all of this information and knowledge into like an end-to-end visual policy. And then we just went with the simplest policy possible And we specified not the goal being like a goal image, but simply like the coordinate of where we want to go, because then this policy will become like a plug and play replacement for like our currently existing like geometric planner, but it consumes images as an input. Uh, this way, we basically had like a training objective that's really embodiment specific, because the imitation learning data is obviously for a single embodiment that we collected. And the geometric planner here is specifically for our case was extremely well tuned for like the legged robot. So basically where a geometric planner tells you to go, you can really go with that system, because like there's so much work that people put into like creating those systems before us, but also like Eves did a lot of work to make this like work really well. And then we ended up the kind of like the policy boils down to like inferencing very simple like waypoints in the future that you would like to go. And we specified this as these goal data sets. Just to give you like some quick understanding of a live demo, because this is like one of the big projects I've worked on is the Grand Tour data set. I want to showcase you here a little bit of like how this data looks. So this is like a Foxglove example that's publicly available. But here from, can I? Yeah. Here you can see a little bit our robot moving around, and you can see there's like the front-facing image. We have like up to 3 cameras that you have a super high dynamic range, and we have really good state estimation on that system. So you can see here, for example, how the robot walks around here on a train track and navigates around. That would allow you to kind of build up the geometric representation based on like the different sensory information we have. And then there's like a lot of other like good things that we have available in the data set. So you have like full joint information, you know about the contact sequences. You have a variety of different IMUs that you can use in the data set that allows you to kind of like do these learning applications towards like also having access to like all of the geometric information that comes with this data set. This is just like a little bit of like a teaser or like an advertisement at this point of like we have like such a cool data set that allows us to be significantly higher quality of what we actually want to deploy on systems, but allows us to set these training setups in a nice manner. So if you're interested in that, you can just go on this like Grand Tour webpage, and then you can go around, explore a little bit the data set where we have like everything super well documented for robotics people. So this is done for robotics people, for robotics people. So you can read about like which different sensors we have here available on that system. But also you can scroll a little bit through this data. So we deployed the robot in like 50 different or 49 different environments here all across Switzerland. And you can just click on like a single example. So for example, if we want to see here like a deployment in like at a different site here on top of like one of the highest mountains in Switzerland, you can just click on this and you have kind of like a YouTube preview video available of like how the deployment looks, what the environment looked like with the different geometric data. And then if this is useful for you, you can use this quite easily, and it's fully open source license that you can build a startup based on this, but also you can use it in all of your research projects. And then there's a lot of work being done on like state estimation and other things based on this Grand Tour data set. But just to give you some understanding of why we thought, okay, we can actually do better in terms of creating a goal, is because we have access to such a nice data set now for establishing this. Uh, yeah, so here just this is like again this understanding of we can train the system on these teleoperated goals, or we can train the system on these random goals that we sample based on the geometric data. Um, and by doing so, we can result then in a data set where we only have, let's say, like 6 to 10 hours of real world data, but we can add 2000 hours of like synthetic data that we can ensure that the action diversity is actually given, compared to like all the other data sets that are across all of these different embodiments and only cover like a few 10 or 50 or 100 hours. Nowadays, there's like some data sets that are actually larger, but they, for example, wouldn't fit like kind of like the a specific embodiment that we're looking at with like a legged robot. So like I think the lessons of this project is really like you need to be smart about what you do with the data that you have available, and specifically under assumption we will be not self-driving where we have access to infinite amount of data. So here you can see then a little bit like of the performance of that system, of that it's really nicely at like estimating kind of where you can go with an environment, and from a single camera already become embodiment specific. So here I pulled together like quite some old slides. So actually this system even improved quite a bit further. We added like a version where you can have 3 cameras, deployed it in closed loop of the robot, and this work is currently like under review for RSS. But I think really we made like the correct step of identifying like some key things in terms of what matters if you want to train these like visual policies that directly predict you where you should go within an environment from a single image. I think we're actively working on like expanding there some ideas. One of the key lessons also was that we can look at here different metrics. So this is like this standard metric of success rate divided by inverse path length. And we could see that when we add basically more training environments, we are constantly getting better. So the diversity of environments, if we go to 41 environments that we trained on a graph, we get better if we use the augmented or the teleoperated data set. But we can always see that there's quite a big gap between kind of like the teleoperated data set and with the augmentation. So the fun thing is we can either collect data from 41 environments, uh, or we can kind of collect data from one environment and add our augmentation with this, and we result in the same performance. So kind of like collecting more and more data is definitely like the way to go. So we see some scaling laws here, but basically we get like a huge performance increase by just adding like this augmentation that also scales then across the environments, which was a very cool finding of this system here. We also looked at like how many training samples should we get, or like how many additional data should we collect, and we found that actually creating like 10 additional training data sets or mixing it up in this ratio 10 to 1 was actually pretty good. So if we go to 1 to 1, we got a benefit, but then if we go slightly higher and increase the diversity of actions, we end up with like a pretty good and solid performance. Uh, Okay. Then I want to like yeah, maybe anyone having some questions with regards to like this work, or yeah. Otherwise, I'm also happy to just continue, and we continue a little bit like this path of like seeing like how we can move from kind of like this teleoperation towards here, moving a little bit more towards like language conditioning on of those systems, because this we basically fully neglected that other people have seen that we can do this language conditioning. And here, basically, like this another student that worked together with us from KIT and ETH. Was the idea that will be presented at ICRA now. Here was the idea that actually like a lot of navigation behaviors can be described already by drawing traces or like these lines within images. If we have access to good images, most likely we can define nearly all tasks based on this image space. So we thought about actually, okay, how good are currently like vision language models based on it? And we looked at these traces because you can specify a lot of different motions within these traces in the images. And I would argue you can solve like 99% of the tasks. And we wanted to understand, given that a human can draw those traces for different embodiments quite reliable, where we can just ask like a given task, like follow the road to the end for like a bike or for like a human, it should kind of like interpret the image and then provide us the correct trace. Or for example, like go downstairs, we would like the robot to, our elect robot to take basically a stairs and our like wheel system to take the elevator. Uh, we wanted to understand like how well are actually like vision language models doing at this task. And what we set up for this is actually like then here a benchmark where we had over like 1,000 of those questions where we formulated this kind of like navigation problem as a visual question answering situation where we annotated over 3,000 manual traces within images that specify like how a legged robot, how a like bike, how a human would behave in navigating these environments, and introduced a metric that basically measures how well does a language model align with human preferences. So here in this case, the metric is actually the lower it's better. And we saw that kind of like these models here are still performing quite bad compared to a human. So a human gets a score where lower is better in this old slide set for like a 1,200. But these frontier models are actually like closing the gap, but there's still like a huge discrepancy between frontier models and actually what we are achieving right now. So there's a huge kind of like assessment that we had for like all of these like vision language models that point us towards this direction of like there's some promising understanding of the scene, but it's still not at the level of a human here. We also looked a little bit at like these failure cases when these systems work well and when these systems fail. Um, and we found basically like different metrics that we tried to tag for like these different images. So for example, are there challenges around visibility, accessibility, dynamic obstacles, and others? And the interesting part that we kind of found is that these models either are uniformly good or suck uniformly. So if a model is bad across like one specific axis, then they're most likely bad across all axes. And with this, we could kind of like evaluate very nicely of like how good is which system performing. And we found really that there's still like a huge gap between human experts. And when Gemini 2.5 Pro came out, it was like a huge jump. So I would be really interested, or like we're gonna rerun these evaluations like on kind of like a 3 month basis or 6 month basis of like keeping track of how good the frontier models are doing. But also we found that kind of by fine tuning like a Qwen 3 VL model or 3.5 VL model on such a task where we provide enough training examples, they actually generalize and do so much better. So we are currently looking at how can we integrate such a trace prediction into like the robotics control stack by having all of these capabilities of this vision language model preserved when it comes specifically to this like task following based on natural language, which we think is like a crucial capability for the robots to have in the future. Uh, yeah. Maybe also questions on that side. Otherwise, here there's also everything available on Hugging Face, and there's like some project pages associated with that. So I will obviously link this maybe not after the seminar in some email that can be shared. Yeah.
So, just a quick question. I think maybe the next slides you can go, you talk about is the implicit, explicit model. So I assume several works you presented so far are more on the explicit side.
Yeah.
Is that right?
Exactly. Yeah. So
Okay.
I think like the next thing will be like on the implicit side. Yeah.
Okay. Okay. Cool.
Awesome. Yeah, so all of these things have been very much kind of like either we try to learn like a policy or we try like okay, we have tried to learn like a policy, we have seen like some other works, but I want to like talk here a little bit on kind of like this implicit side on like the dynamics model learning, and then I can showcase we have time till 1 p.m., right? Or like 11 p.m. for me. So we have 10 more minutes if I'm not
We can go to 2:15 usually,
Okay,
Yeah,
perfect. Okay,
I
this
would
is
say.
great. And
Yeah.
we have a little bit of time. So I want to show you a case, this kind of like idea of like training like a dynamics model. And I think that was like, wait, do I have the slides for? Oh, now let me see that I get the slides for the dynamics model because bup, bup, let me see where I have them. I would like to showcase you that. Yeah. Okay. Yeah, let's look at the dynamics model. I think that's a quite cool work. So like this was the dynamics model learning work where this was like accepted last year to RSS, where the idea is can we learn actually a dynamics model? And we have seen still when we deploy our robots in these different scenarios that we very often end up with kind of like failure cases, like here the snow, the loose grass, or these entanglements here that are still not captured really by kind of like the current simulation environments. So what we tried to do in that work is actually, we have like automatic jumping. Okay. We try to have like a lot of like data collected from simulation combined with data collected in the real world to train a model that predicts us kind of like given the proprioceptive history of of your states, but also your exteroception of your environment, so like a height scan, to predict us the future poses and a risk or like a failure probability of how likely it is for the system to fail in the future, given a sequence of actions. So the nice thing by formulating such a problem is that we can input basically a sequence of actions and then understanding where our system will end up in terms of its future pose, but also what's the probability of failure for that system. To give you here some notion of how this looks, it's basically we can see here that the robot uh, tries to plan a different path where we have kind of like a prediction for if it's safe or unsafe based on if the path is blue or red. And we can see that we can now compare the simulation against our actual model here. I'm really sorry because here's like still the automatic kind of like uh, slide forwarding active, given that I haven't checked the slides. But the idea is you see basically three paths here to explain this really well. We see the orange path. This is the ground truth that when you actually roll out the full physics simulator, we see the blue path. This is the prediction of our model, or the red path is the prediction of our model. Uh, and then we see the purple path. This purple path is our baseline. This will correspond to simply integrating all of your commands or of your action commands in terms of velocities when you want to walk as a model to predict the position of where you end up with. And you can see that there's a discrepancy between here this purple path and the actual predictions of our model or where the robot will actually end up with. And what we found is that our model gets really well at kind of estimating when these collisions happen, but also estimating more accurately of like how the robot would behave when interacting or walking on those stairs. which is a pretty cool thing. So now we are not reliant anymore of doing like a traversability analysis, but we have a module that we can ask, like, given a certain set of actions for the next kind of like 5 seconds, where will the robot be ending up in? And this way, we can basically use this model to do planning with it. So here we can see like a robot walking around in our lab, and we sim to real transfer that model, and we can see that those paths are actually predicted correctly of like accounting for like collisions and other hazards that we're having across those scenes. We also tried that model then to see if it accounts for like these slippery behaviors in other models where we can see that those predictions become like significantly lower. And we saw that we see like a big improvement in terms of like performance of like 30% roughly if we train on real and simulated data. So like the idea is basically we have here a model that we can use to roll out our dynamics via the model to obtain like where's the final position of the robot. And we have a really simple reward function available that tells us like, okay, did we succeed or not at after like ending up at a certain position. And this one we can, sorry for that. This one we can then basically these kind of actions that we provided to the system, we can then perturb and kind of like use black box optimization to set a new set of actions that we feed through this model here to obtain like a new goal or like a new position where the robot will end up with, to find like what would be the optimal action to take right now that leads us as closely as possible towards this goal without knowing anything or specifying anything about the traversability, because this traversability is captured here by this forward dynamics model that defines at which location will the robot end up with in the end. So you can see here these different paths with different colors. And basically the one path that we would take is the one that leads us the closest towards the goal while ensuring that it's safe and we have like a low risk. Uh, so this we basically showcase like then also that it kind of functions nicely in like this closed loop example here to walk up those stairs. Um, and we can then navigate like upstairs here across like different scenarios. Uh, we also ran this full system then in kind of like closed loop on the robot itself to navigate like around at our terrace here. That showcases always like the prediction of like where the robot tries to navigate, and we provide different goals throughout that environment that the robot then follows and avoids all kind of like geometric obstacles here, but also accounts slightly for things like slippage and other things based on its proprioceptive data here in this setting. Yeah, this is like one of the works that I wanted to showcase for the kind of like the implicit way of learning dynamics. And then maybe I think like it's would be great to showcase you the work about like wide visual navigation. I think that your group has been also like looking into and expanding on, if I'm not mistaken. If you don't have any other questions for the forward dynamics model here. Yeah.
I have one
I
quick
have
question.
some good questions. You
Okay.
can
Yeah,
go
sure.
first.
Yeah, go ahead.
Okay. Okay. Yeah, I have two questions. First question is, if I understood correctly, you the exert subsystem that you're using here is mostly like geometrical high scan or depth camera, and
Yeah.
then it requires massive amount of simulation deployment. So
Yeah.
how I wonder if it could scale up for the visual RGB input for this model.
Yeah. Yeah, it's a great question. So in this way, for this work, we kind of went with geometry and this proprioceptive data for specifically the reason that we have kind of like a really hard time simulating correctly like physical or like realistic scenes. And it's very hard for us to model this interaction between how the scene looks and how it physically feels
Yeah.
to interact with that scene. When we just go to RGB, I think like potentially such a work could work if we have like a very big amount of like real world data available. But then we very often come to this problem that you end up very quickly like out of distribution. But with kind of like RGB features, I could see like some potential that they generalize based on these like pre-trained models. Uh, but we found that it's just more robust to kind of try to infer this based on your proprioception after interacting, but then you don't cover all of the risks that you would have. And specifically in the real world, we always have to deploy the robot in a way that it's very, very safe. So we can't have any failure. So we would kind of require to simulate failure cases also in simulation from that would correspond to visual observations. And this is something that is just like very hard to do right now. So we did not think about
Right,
like
right.
generalizing this to geometry just because of like the data collection in the real world will be mostly always safe and your system will be in a nice state. Yeah.
Yeah, thank you. Yeah, I was also thinking about how we can overcome that problem. And I think I have the second question, and it is for this kind of implicit models, I think it would work well for relatively short-term range of navigation, like local planning level. And I wonder if it could be used for, it could completely replace the whole navigation stack, including the global planning that sometimes requires very, very large detouring. And I wonder if this kind of implicit model can reason about that kind of like kind of overcoming kind of local optima of the shortcut.
Yeah. Yeah, I think something that I'm quite interested in that we see more and more is kind of like this level of hierarchical dynamics models or models that operate at different kind of fidelities and different scales, right? I feel there's like quite some big promise when you want to like overcome kind of like uh, certain assumptions on like a global level that you have like a dynamics model potentially like working in language space that kind of like could roll out how your robot will behave in language, but also then like kind of like this dynamical interaction on a shorter horizon, but also basically combining models together that try to mimic like what should be the future state of your robot, something that goes from like joint level to like position level to something more abstract on like kind of like language level of what you could behave that you can use for doing some sort of planning across all of those different levels of hierarchical understanding of your scene. I think that would be very interested. With regards to answering your question, I'm not sure if this answered your question. Uh, yeah,
I think it's an open question, and
yeah.
yeah, nice to hear yourself. Thank you.
Okay, awesome, awesome. Yeah, we can. So I can maybe like take this like I can take this step back and show you a little bit of work on like this traversability estimation that your group is most likely super aware with. So if you want, I can walk you through this, or we can look at some other works that we have done with respect to like some newer works, for example. This depends on what you think is like most interesting for you also.
Could I ask one more question about
Yeah,
robot dynamics work?
sure.
I guess you work not just predict the future state of the robot, but I think your model also has some implicit right, how to say, cost function or reward function,
Yeah,
understanding, right? I think because like when you show the video of the robot's pose prediction,
yeah,
so when you like send the like maybe straight velocity command, but the model can understand like how to detail the
yeah,
object.
yeah,
Um, but so question is like, so how do you use this model for the planning?
yeah,
Because I think this model is not just the date prediction, but has some kind of cost function in the loop.
yeah,
So even if you input some, because like when you um plan with the model, I guess you roll out some like multiple paths of the trajectory, and then you evaluate each trajectory and then produce
yeah,
the action if you do that in the MPPI style. But I was wondering like how this process works.
yeah, yeah.
How does the planning works in this
Yeah,
case?
exactly. This is an excellent question. Let me see if I have like the better slide for that. I think no, this is yeah, this might be like the best slide that I have for here. Okay, yeah, let me see. This is a little bit easier. So, okay, the idea is we have this like train forward dynamics model, and we get the observation as an input, and we then get the future poses. And what we try to do is specify the simplest possible reward function. So you can imagine we ask for 1,000 different action sequences that would define like what you do for your next 5 seconds, but we have 1,000 different ones that we sample, or even more. I think like you can run it with like 4,000 action sequences, given that this model is very small. And then we obtain the position of where the robot ends up in the end. And we try to specify the most simplest reward function possible that only has like the post reward. So where will your robot end up with? and what is the risk that you will fail by executing this trajectory, where failure is basically defined as a collision. So this way we have a reward. So we basically need to, for this system to work, for doing like black box optimization, we only need to have a reward and a mechanism to sample actions from. And this we can then do like in this MPPI fashion or in a cross entropy method fashion, where we kind of do a certain perturbation to our action distribution and then try to evaluate, okay, our new set of action distribution that we want to sample from, like what would be the reward of these kind of like new set of actions and how close will they lead us to a goal? And with this like zero order optimization methods, we can then always fit the distribution of possible actions that provide us the lowest cost. So given that these zero order optimization methods work really well, we kind of have like a quick way to sample this online in like an MPC kind of fashion. But this basically, the key thing is it requires you to have like a forward dynamics model that's ultra fast and allows for parallel computing of those trajectories. We need to set up a manually defined reward function. But what we are kind of proud of in this work is that we reduced all of the reward functions to the most basic thing, like will you fail and where will you end up with? Uh, and then if you do like further reward shaping and other things, you can get like better performance potentially out for sample efficiency. But in itself, our model basically allowed us to do this correctly with just this very simple reward function. And then you need to have like the correct way of like how to sample from a distribution. So there you need to set like certain things about your action bounds that you can define based on your capabilities of your robot. So for example, maximum and minimum velocities that guide you which kind of like actions you start out sampling from and what your initial sampling distribution is. But that's basically a huge design choice that goes into like setting up a correct MPPI planner. Uh, I hope that that
So yeah,
answers it.
yeah. So when you train this model, right? I guess you have some pre-trained locomotion policy and then correct the trajectory and then use this trajectory to train this FDM. Wondering what's the data set size you need to correct to train this kind of model?
Yeah, yeah. So we are looking at like around, okay, so each trajectory, we're training around 30 epochs with 40,000 robots,
Mhm.
with 44,000 robots. So this would be like 100,000. So it's around like 100,000 robots walking for like a minute, let's say, or like 30 seconds around that.
Mhm.
So
Mhm.
this gives roughly the size. And then for the real world data that we use for the adaptation, we kind of have only like these 50 kind of like missions that we use for fine-tuning the model. So we kind of like pre-train a lot on like simulated data sets that the model gets really robust. And also how we set up the simulation training is very important because what you want to have is that this forward dynamics model stays always in distribution. So you need to ensure that you train it on the correct set of actions. That means like we collect actually during training, we actually already use the MPPI planner to ask for kind of trajectories to roll out such that we stay in distribution. Because if we ask for trajectories that it has never seen before, this model won't work. So these are the two kind of like data set sources that go in. So we then, after we have done like the big pre-training on simulated data, we kind of can add in with a certain percentage. And I think we, in the end, we figured out that sampling 1-to-1 works reasonably for us for like combining real world and simulated data. And I think this is
Yeah.
something that is not ideal in that work. And we just did something. So there's, I think, like a big possibility to do smarter research because in simulation, we might have the case that our model tells us you will walk like 1 meter
Mhm.
given the same set of inputs. And in the real world, we will discover that you only need to walk like half a meter or you will end up walking 2 meters because you have like some sort of slippage. So there's kind of like unmodeled effects that are happening here. But given that we assume that this forward dynamic model can most likely tell if we're in simulated or real world data, but we just found that this works quite nicely. Yeah. So because like I think like the real world data and the simulated data will still look a little bit different, specifically from the height maps that we put in. There will be
Mhm.
like some discrepancy that you can detect. So I think if we would try to train like a small probe of telling us, are we currently facing real world or simulated data, most likely the latent features of the forward dynamics models will be able to encode this. Would be my rough guess right now. I think we haven't done any experiments, but I think there's a lot of opportunity to see which sort of data we want to be using here.
Did you mention you used the MPPI during the trajectory correction to
We
train
use the
FDM? Did you mention
MPPI
that?
during the collection of data and simulation. So basically, when we ask for
So
which
you
simulation
okay?
data
So
we
you
use,
operate in the like just use the simulation dynamics to roll out MPPI during the dataset correction,
uh,
or use the
you can do both, I think. You can just like
Mhm.
forward integrate it for the simulation, or you can roll it out with the model. Uh, like what we also did not
But
do
but
is,
you're still you're correcting this data set to train FDM, right? So are you talking about like on policy style running
yeah,
stuff?
no. We did not do like more advanced kind of like options. We really did the most simplest thing. So we did like a forward dynamics model that we just used to roll it out to go to certain goals. So I think we did not close the full loop in terms of like having the forward dynamics model kind of in an on policy style being constantly inferred. I think there's also like a huge way of improvement because like this was done together with like a colleague of mine at NVIDIA. So he could just use a lot of GPUs and then we could just collect a lot of data and also the
Mhm.
simulations are really quick. So we didn't
Mhm.
care really about kind of which data we are using and what's the most sample efficient data to obtain. I think if we had to do this work under severe compute constraints and we actually wanted to only collect data that's useful, we would have like kind of attempted like kind of collecting the data in a more smart way in simulation. For us, we just collected now like a lot of data for the pre-training phase in simulation.
During the pre-training phase, you just set some random goal location and then create a path toward this goal using
Exactly.
MPPI. Okay, okay.
Exactly. This is exactly what we did. And then we basically during the pre-training phase, also we had just like random actions that we tried to execute because this
Mhm.
way we run into some walls. So it was a combination of random actions and random goals for MPPI. Yeah.
I see. I see. Because I thought this work is pretty connected to like the planning using water model, like JPA style water model. I think in your case, maybe future pulse prediction is kind of like a latent space prediction, and your failure rewards is probably termination prediction of the JPA. Um, so I'm wondering um, like what do you think about the connection between your work and the latest like water model
Yeah.
papers?
Yeah,
I,
I was thinking about this. If you can predict the images, right? I think that, I think earlier was asked, if your forward dynamics model can have this word model in the loop, I feel that'll do a lot of,
I fully agree. Super
yeah.
interesting. Yes, absolutely. I think there's the clear connection between kind of like world modeling here, what's happening, and what we are doing. The main difference is that kind of like I'm not sure if kind of I'm not 100% sure if we should go through the full process of reconstructing images to make this decision in the end of like which trajectory should we take or which action should we take in your world model. Well, I see all of these benefits of doing planning and this Jan LeCun kind of like argumentation around those things, and it's super attractive. But it feels currently to run this in closed loop on a robot is super expensive right now, right? Because you actually need to go through the process and generating all of the pixels. So I feel like some planning and kind of like these latent spaces of those models would be super interesting for doing. And
Yeah,
in the
I
end,
mean, Jipper don't necessarily decode the image. You
yeah,
don't need to decode the image in
yeah.
the I
Yeah,
mean,
yeah. There's like this world navigation models by Amir Bar, I think.
Mhm.
Uh, and I did something similar with kind of like training a diffusion model or like a model to kind of generate the images based on the future trajectories of where these systems are going. Uh, and I think it's very interesting. And if you can do it in a latent space, it's even better. Yeah, yeah. But it's really to
Okay.
think like what can
Yeah.
we scale sufficiently, right, in terms of where we have enough training data available for certain tasks. Uh, yeah.
also I want to ask, so if you wanna
Sorry, Jun. So let me jump in a little bit. I have another meeting. I have to jump off,
Yeah.
in 2, 3 minutes. But I think this is a very interesting talk. I mean, Eunice, if you have time, I think some of my students will be here, very interested. Maybe you guys can continue for another 10, 15 minutes. you guys can keep going. And there's also questions in the chats. I think Alfred asked some questions. But so I'll leave it to you to decide if you want to, present more of your future works, or we can keep, like having,
No, no,
Q&A like
I think
this.
having a chat would be perfect.
Okay.
Yeah,
Yeah.
yeah, I think this is great. Thanks a lot for coming by and giving me the opportunity to talk.
Okay. Yeah,
Really good
let's
questions.
keep going, and I might sign off in a few minutes, but I think this is great. Yeah, let's keep going. Yeah.
Okay, awesome. Thanks. Yeah,
Okay.
yeah. Feel free to ask. Or where were we? I think I lost my train of thought.
Yeah. Yeah. So going back to the question. So if you want to let's say extend this work to like let's say local manipulation of the human and robots, right? How would you set up the data collection pipeline? Because like maybe for navigation, maybe random sampling, the goal state might be straightforward, but for local manipulation, probably end effector, I mean, task space
Yeah,
is a bit more complex, right? So how would you like set up the training, like
yeah.
collecting data set?
One of my first ideas is you would start out with kind of like some of the large human data sets retargeted to your robot, and then you obtain kind of like some rough references that are physically not realistic in first place. Um, so that would be like one source of data that could come in is actually like something retargeted from human motion that I think would be interesting. Then there could be like another level of data that could come in from actually like trying to like train already policies on kind of like tracking the human reference data. Uh,
Mm-hmm.
I think that would be also on source. I think you can't do sampling, right? There's no way of like doing like pink noise
Yeah.
sampling, something like
Mm-hmm.
MPPI to collect
Mm-hmm.
any sort of data. So you would like
Yeah.
to have some sort of expert policies. I think the interesting part that I've seen for kind of like whole body locomotion or locomanipulation, when it comes to like the reference tracking, there's this work that's tracking any reference under any disturbance or so, if you're familiar with that. Uh, this this work has like a huge part of it involves training a world model. So like training actually the forward dynamics model as part of the policy training. So I think for some parts, actually training kind of like the policy and this model together could be even more useful.
Mm-hmm.
And they
Mm-hmm.
showcase that you can put in like 5 seconds of past history of the robot and then predict the next 1 or 2 seconds of like how the robot will be moving. So that's actually like a quite big horizon already of like future prediction. And with this 5 seconds of looking back in history, you can basically infer a lot of like these disturbances, your parameters of your robot, your PD gains, or your differences in stiffness and damping of your joints. You can all infer this to make your future prediction. So I think I would look specifically for whole body work at kind of like training this in combination with the policy itself. Because also like in the end, this forward dynamics model, we can just distill it into a policy if we don't want to run MPPI. Yeah.
Thank you.
I think I just shared that paper in the chat. I'm not sure if that's the one you're talking about, but that sounds interesting.
Yeah, exactly. Yeah, I think it's that paper that has like this component of training, like, is it that paper? Yeah, that looks great. Yeah. So you have your current state, and then you try to predict based on a world model, like what's your future state of kind of your environment. And I think they have like a big aspect towards that, with kind of like training multiple different policies to kind of do different tasks and then distill it into one, but have like kind of like a very good, strong representation available based on this world model that predicts you how your future state of your system evolves. Like nowadays, we like if we would be in a current if we would have written this paper today, most likely people would call this a world model, what we trained back there, and was just like we took the dynamics model learning approach or like the formulation of that. But I think the difference is very little. Yeah. Yeah. I think
Um,
yeah. Feel free to ask. Yeah. So,
yeah, thank you. I have a question like other than research, but um, I have been following your works during your PhD, and I'll say honestly, I was pretty impressed by your productivity. Like I saw you published many papers and during your PhD. And actually, Max and I are mainly working on traversability and navigation in our group. And working on navigation, I feel like it's kind of it requires a whole system to be prepared, like from the global planning, estimation, mapping, all the low-level controllers. And it's very hard and it's pretty tough to prepare all the things and sometimes slow down my productivity. And I just want, so I wonder how you maintain your productivity and yeah.
Yeah, I can comment a little bit. So basically, I think during my PhD, I was very fortunate in the first place. So I came into a lab where we kind of had a quite robust setup of robots. So we kind of had like running robots before I joined. There was still like a huge tech stack, and there was some sort of tech debt that we always had to address. But we were like a very big group. But I would say we were like everybody was very motivated and also like worked together extremely well with each other. At ETH Zurich, we have like this one unique benefit is I had the opportunity to work with like extremely excellent master students throughout my time. So like a lot of master students are super highly motivated to do like a master thesis, so like a 6 or 9 months project, and then work on this and kind of spend a lot of effort of kind of trying to do like first time doing like something for research in that regards. So this was like super productive by working with like super many like smart people. At the same time, we were basically not resource bounded, I would say. A lot of other labs are more resource bounded. Like I can just give you like some examples. We did like, for example, here this data set work, and I'm very grateful for my advisor. So I think Marco is like the best person when it comes to like. By the way, is this recorded still, or should we maybe cut the recording at that point? Uh,
I can
but
stop
like,
it.
yeah. So